All right, ladies and gentlemen, so in this lesson, what we're going to be discussing are matrices. Matrices are something that is kind of a natural evolution of what we have been doing with systems of equations, where a system of equations, you originally kind of learn about what they are and how they're used back in Algebra 1, used again in Algebra 2, and what we've done in this course is we've taken the concept of systems of equations and we've expanded it from a normal 2 by 2 system to a 3 by 3 system, and it could actually get more complicated than that. You could have bigger systems than what we have algebraically, what we've been doing. Now, the problem is that the bigger the system, the more variables, the more equations there are, the harder it is to actually do stuff with them. And matrices is a way of kind of organizing them and actually uh, doing operations with them that's actually a lot more efficient and simple than the traditional algebraic process will be. Now, some of you, as you watch through this video and some of the things that we're going to be doing with matrices may disagree, but that is kind of the idea behind it. Now, a matrix, what we do is, we kind of just put it in a rectangular form where we say something like this, where we have those square brackets and inside of it are numbers, okay, whatever those numbers happens to be. And it's named with a capital letter. Now, there's nothing saying that it has to be a particular letter, so I'm going to call this I'm going to call this matrix C for college algebra. So it's just something that whatever letter that you want it to be, that's what it is. Now, typically, a way of kind of keeping track of things, normally what people do when you're working with matrices, uh, especially like multiple matrices at a time, is the way that they keep track of them is they just kind of do it alphabetically, where the first one is matrix A, the second one is matrix B, the third one is matrix C, and so on. But there's nothing saying that it has to be done that way. It's just a kind of way of keeping things organized. So the size of a matrix is depending on how many rows and columns that it has. So in this particular example that I have up on the board, well, there's 2 rows and there's 2 columns. Now, what we're going to be doing with rows and columns is, well, one of the things that we want to know is how do you identify something in a matrix? So here we have matrix A. It has 2 rows and 3 columns. So we refer to matrix A as a 2 by 3 matrix because it has 2 rows and 3 columns. Now, the entries in the matrix are represented with this kind of notation where we use the lowercase letter of however we named the function. So if we were talking with function b, we would say lowercase b with a subscript of I and j. If we were talking about matrix, L, we would say a lowercase l with a subscript of I and j. The A is going to be whatever that lowercase letter, it's going to match with whatever the matrix itself was called. Now, the I of the subscript of that notation is telling you that's the number that of the row that that particular entry comes from, and the J is the column. Okay, so in this case, the example A23, well, that says look at row 2, column 3, and in that spot is the -5. So that's how we're identifying those values. Now, the reason why that's kind of important is matrices are used pretty much in anything that's going to use digital imaging. So anytime you take a picture with your phone or your camera, or you store you do something with it on a computer, you're changing. The image is stored as a matrix, meaning like in row 10, column 21, that pixel has to be red. So that's the number 5. So that's how the computer knows to change it. And if you want to adjust the color or the contrast, or use one of your face swapping apps or something like that, it's all really kind of controlled by matrices. The way that your devices handle those is by, well, we're saying, here's this matrix, do this thing to the matrix, and that's how the picture winds up getting changed. So here what we're being asked to do is to determine the size of the matrix and identify whatever the entry that's in the first row in the second column. So here, matrix B, we'd say that this is a 2 by 2 matrix because it has 2 rows and 2 columns. So what we're asked to identify is what is in the first row and the second column. So in the first row, second column, we have a 3. So B of 12, we would say, well, that's a 3. And so in matrix C, here we have 3 rows and 2 columns. So we would say 3 by 2. Matrix C is a 3 by 2 matrix. And again, we would have kind of a lowercase c. And again, the first row, second column. First row, second column in this case is a, oh, pardon me, -7. So that's kind of what we're looking at as far as, you know, how we determine the size of the matrix is by how many rows and columns that it is. And by picking a particular entry, we say we have that first number that's called that I, that tells you the row, and the second number row, and that number tells you the column. So that is how we determine the size of a matrix and where something is in a matrix. So the next thing that we're going to be talking about is the diagonal of a matrix. Now, certain matrices are known as square matrices because they have the same number of rows and columns, and so that it actually looks like a square. And square matrices are unique in the fact that what we're going to be doing is we're going to be able to identify a diagonal entry. Now, diagonal entries, there's actually, anybody that's played tic-tac-toe knows that there's more than one way that you can do a diagonal. Now, in this case, the diagonal of a square matrix is always going to be done in the same way. It goes from the top left corner to whatever is in the lower right corner. And what this is telling you here in the bottom, in the brackets here, is that where it says I is equal to j, basically the number of rows has to be equal to the number of columns in order for it to be a square matrix. And that's kind of what that last notation is talking about, but it's not something that we're really going to be doing a whole lot with. I mean, I think it's pretty obvious. Normally when you look at something, you can tell, oh yeah, it has 4 rows and 4 columns, so it's a square matrix. It's not something that you have to notate that secondary way. So here, what we're asked to do is identify the diagonal entries of this particular square matrix. So I'm going to call this square matrix, let's call it S for square. I don't know, just because. So what it's asking us to do, it says identify the diagonal entries. Now, remember, you can have more than one diagonal, obviously, but for a square matrix, we're only concerned with looking at whatever goes from the top left corner to the bottom right corner. So the diagonal entries of this particular square matrix would be 2, 4, and -2. And that's pretty much it as far as what it's asking you to do, and it just says identify the diagonal entries. Now, this is kind of where I was mentioning earlier in the presentation at the very beginning, how matrices are kind of being used to marry what we've been doing with system of equations. And from here, this is really, anything larger than what we have been doing in class, where we have a matrix that has 3 variables with 3 unknowns, or 3 equations with 3 unknowns. We want to start doing it as a matrix because it just becomes more efficient that way than trying to do it in an algebraic process. So this is kind of what we would have, seen in class, where, we said solve for x, y, and z. Well, what we're going to do is we're going to break this particular system of equations up into 2 matrices. One matrix, the bigger matrix, is made up of all of the coefficients of whatever the equations happen to be. So whatever number A is, that's the first number in the first column. Whatever number B is, that's the second number in the row, and then C. So all we're doing is you can see that this row 1 corresponds to the coefficients in equation 1, and the first letter, the top letter of the constant matrix, again, this is row 1, and it also gives you something from equation 1. So the second row comes from the second equation. The third row of the matrix comes from the third equation, and so on. And so what I just want to show you how they're doing this stuff here. So what we're going to be doing is we're going to actually be taking systems of equations like this, stuff that we have been doing solving algebraically. We're going to start solving them with matrix. So you need to know how to take a system of equations and write it as a matrix instead. So that's what this is showing you here. Now, just like when it came to, say, I don't know, polynomial division, whether we did long division or synthetic division, if there's something that was missing in the polynomial, we had to substitute, we had to notate that with a 0 whenever we actually did our substitution to do our division. Well, the same thing here. If there is something missing in a system of equations, like say the x variable is missing in the second equation, well, we would substitute that with a 0 when we actually make the matrix. Okay, and what this last thing is telling you here, the coefficients are always in order of x, y, z. So whatever the matrix happens to be, we had the equation like, I don't know, 3x plus 2y minus 5z. That's what it's telling you. We're always going to put them in order from left to right. The coefficients of x, the coefficient of y, and the coefficient of z, and so on. And we'll do that for all of our rows. All right, so now this last thing that you're seeing here is what is known as an augmented matrix. An augmented matrix is taking the constant matrix and it's putting it together with the, oops, I wrote that backwards. Not the constant matrix. This is the coefficient matrix. Oh, no, I didn't mean to have the eraser that big. That's okay. So here, this whole thing, that square matrix right there, that is the coefficient matrix. And this 3x1 matrix right here, this is the constant matrix, meaning that's like the answers, where equation 1 is equal to this, equation 2 is equal to this. Okay, now we were going to be creating these types of matrices so that way we can try solving them, or maybe writing the equations of them from the matrix to what the system would be that generated it, and go from there. So here in this example, what we're being asked to do is says, okay, form an augmented matrix for this particular system and name the diagonal entries. All right, so let's go ahead and just start with the matrix. Now, the first row of the matrix corresponds with the first equation of the system. So since we write them in order of x, y, and z, the coefficient of x is a positive 2, the coefficient of y is a negative 1, and the coefficient of z is a positive 3. And then I can give myself that vertical bar there to divide the coefficient matrix from the constant matrix, and the constant of equation 1 is the number 14. Okay, and we're going to just do that for the other two rows as well. So the coefficient of x in the second equation is 1, it's 2 for y, and negative 1 for z, and the constant for that equation is negative 3. So here, the coefficient of x is 4. In equation 3, y is missing, so I'm going to put a 0 there. And the coefficient of z is negative 2, and its constant is a positive 2. So here is the first thing that it's asking us to do, is to form the augmented matrix. Now, it didn't ask us to name it, so we're not going to call it like matrix A or B or anything like that. And so the diagonal entries The diagonal entries are going to come from the coefficient matrix because that's the square matrix. So the diagonal entries go from the top left to the bottom right. So that would be a positive 2, and a negative 2. All right. So again, same thing. This is what it's asking us to do. It's asking us to write the corresponding system of equations. So instead of giving us a system and asking us to write an augmented matrix for it, here they're providing us an augmented matrix and they're asking us to create the system for it. Now, what it's asking us to do after we make the system is to solve it. What are the values of x, y, and z? So row 1 of the system corresponds to equation 1 of the row 1 of the matrix corresponds to row 1 of the system. So the first equation that we'll have will be 1x plus 5y plus 1/2 z is equal to negative 24. And we'll do that same thing for the other two rows of the matrix. So the x variable in equation 2, or row 2 I should say, is a 0. So we're not going to put anything for x in equation 2. We're going to say 1y plus 3/4 z will be equal to a negative 2. And since in the third row of the matrix, the x and the y variables are 0, or coefficients are 0, we're not going to have an x or y in the third row, and we're going to just say that 1z is equal to 8. So this is the system of equations that was generated from the augmented matrix, and now what we're asked to do is solve it. What are the values of x, y, and z? So if you notice, equation 3 already has z solved for us. We know that z is equal to 8. So I'm going to take this 8, and I'm going to substitute it into equation 2 so that way I can figure out what y is. And so I'll say y is equal to, oops, sorry, not y is equal to, but y plus 3/4. So we'll say y plus 3/4 times 8 is equal to negative 2. Okay, so let's see what we hit here. So y plus 3/4, okay, well, that is going to 3/4 times 8, that's just a 6. And move the 6 over through substitution, and we get y to be equal to a negative 8. So now I'm going to take this, I'm going to substitute y and z Now I'm going to take the values that I have for y and z, and I'm going to go to equation 1, which I'll need to use this side of the board for, and I'm going to substitute those into equation 1. So equation 1 is just x plus 5, y plus 1/2 z equals negative 24. So let's go ahead and substitute our numbers in here. So x plus 5 times negative 8 plus 1/2 times positive 8. So 5 times negative 8 is a negative 40, and half of 8 is 4. And so negative 40 plus 4 gives you x minus 36 to be equal to negative 24. And then move the negative 36 over through addition, and I will get x to be equal to a positive 12. So the solution to the system that was generated from the augmented matrix would be 12 for x, negative 8 for y, and a positive 8 for z. Now this is what we're ultimately going to be winding up doing. We're going to be taking a 3x3 system of equations, and we're going to be generating something here, what is known as an augmented matrix. Now, if you notice, the fact that I have a 0 here, a 0 here, and a 0 here, that is not on accident, okay? And the whole reason that we did it that way is so that way when we set up the system, I will automatically know that z is going to be equal to this number, and that allows me to go back, substitute that into equation 2 to get y, and then therefore go back to equation 1 and get what x is. Now the thing is that this augmented matrix, where that bottom left corner is 0, 0, 0 the way it is, what we're going to be doing is we're going to have to know how to make that ourselves, okay? And that's where we're getting into here. What up at the top it says elementary row operations. Now, row operations are similar to what you have done using the elimination method when you're just solving a system of equations. What you're doing is you're trying to make something equal to 0. So you're going to kind of multiply equations by certain numbers, and then, you're going to multiply rows by certain numbers and then add them to another row. So that way when you're done, well, we're going to wind up with an augmented matrix that kind of had that same pattern of zeros in the lower left corner, so that way we can solve a system of equations. So, just like what we did before with our 3x3 systems, we had to eliminate, x or y or z. We had to pick something and eliminate it completely, but we had to do that 2 times in order to have a simpler 2x2 system. Well, this is the same concept, except instead of making a 2x2 system, we're trying to take a square matrix and eliminate the x variable from equation 2 and the x and the y variable from equation 3. And that's how we're going to use matrices initially to solve systems of equations. Now, before we get into that, let's take a look at, well, let's just see, what are we doing? So what you're seeing here to the right of the matrix, so the matrix that you have itself is a matrix of a normal system of equations, where I would say like 7x plus 4y is equal to 3 for the first row, and 4x minus 8y is equal to 12 for the second row. Well, what we're asked to do, the stuff that you're seeing here, these are basic row operations. The first row, what it's telling you to do, we're going to look at the top first and the bottom second. We're going to kind of do them in that order. So what we're going to do here, let's just go ahead and take the matrix and say 7, 4, and 3, 4, -8, and 12. We're going to take the augmented matrix, and let's just take it one step at a time. So what this is telling us to do, and the row operations that you're seeing here, they don't have to be on the right of the matrix. They could be on the left side of the matrix as well. What it's telling us to do, it says take row 2 and multiply everything in row 2 by 1/4. And then it's saying that arrow is telling you to replace whatever you got, replace that into row 2 again. So we're going to take everything in row 2, multiply it by 1/4, and then whatever we get as our new numbers, we're going to rewrite the matrix with those new numbers in place of row 2. So 1/4 times 4 is 1, and 1/4 of -8 is -2, and 1/4 of the 12 is 3. So we're going to take this new row, and I'm going to replace it with what was originally in row 2, because that's what this is kind of telling me to do. All right, so now we're going to say 7, 4, and the 3 for the first row, and we're going to replace row 2 with the new stuff that we had, the 1, the -2, and the +3. Okay, so here is our new matrix that we got after we did one row operation. Okay, well now what it's telling us to do here, the second thing is saying, okay, well now take this new matrix that you had, and it says row 1 with the little double arrows on the side, and it says row 2. Well, basically what that's telling you to do is it says take whatever's in row 1 and put it in row 2, and take whatever's in row 2 and put it in row 1. We're just kind of taking those two things and making them trade places. So that's going to give us a 1 and negative 2 with a 3 in row 1, and the 7, the 4, and its positive 3 go to row 2. And so the final matrix that we should have after doing those two operations is what you see there in green. So the matrix operations, they operate on the same principle that we have been doing with when we're doing kind of the elimination method with systems of equations. And what we're wanting to do with these ultimately is we're wanting to be able to take our row operations here and kind of take a square matrix that has 3 rows and 3 columns and kind of eliminate the x, y, and the z variables, I'm sorry, the x and the y variables from equation 1 and 2 like we saw in that last example. Okay, and this is kind of what we're looking at here. All right, so what we're kind of looking at here is this is a normal kind of 3 by 3 system of equations where we have 2x plus y minus z is equal to negative 3 and so on. But what we're not asked to create the system of equations here. What we're asked to do is this is what we're leading up to. We're going to take this matrix that was created from a system of equations and try to work it in such a way that we're going to have the 3 here, the 4 here, and the 3 here. What we're ultimately wanting to do is make those 3 numbers 0, so that way we could actually at some point go back and solve what x, y, and z are. Okay, and this is really what people would have to do, and you're going to see it is going to be a little complicated at first, but once you do it a couple times, you'll be okay. Now, the first row operation that we're seeing, it says take row 1 and multiply everything in row 1 by a negative 3, and take everything in row 2 and multiply it by a 2, and then add them together. And whatever we get, we're going to put that into row 2. So here, take everything here, multiply it by a negative 3, take everything here, and multiply it by a, let me erase this arrow here. We don't need those now. Multiply this by a negative 2. And the whole point is what you're seeing is if I multiply the negative 3 up top and the negative 2, oops, not negative 2, positive 2. What we're trying to do is that if we do our multiplications, we're going to have a negative 6 in the top row and a positive 6 in the bottom row, which is going to give me the 0 where that 3 is right now, and that's kind of what we're going for. So negative 3 times the 2, that gives me a negative 6, and a negative 3, and a positive 3, and a positive 9, because we have to multiply it to everything just like we did when we were solving these through elimination when they were systems. So now multiply the 2 through the second row, and I'll get a positive 6, a positive 2, another positive 2, and a 0. And we're going to add those two together. So you see here, they give me 0. Here I get a negative 1. Here I get a positive 5 and a 9. And this is now row 2. Okay? So I'm going to just kind of keep going down. We didn't actually change anything in the first row. We multiplied it there to do something to get a new value of row 2, but we're not actually going to change anything in row 1 when we write it out. So we're going to say 2, 1, negative 1, and the negative 3 that was in row 1 originally. And now we're going to take the numbers that we got a second ago and put them in row 2 now. So here I have a 0, a negative 1, a 5, and the 9. Now we still haven't done anything to row 3, so we'll put that in as kind of, normally what it is. 4, 3, 2, and 3 in this case, with the bar to separate the constant from the coefficient matrix. All right, so now let's go ahead and do this next operation here. So here, looking at this one, this says, okay, take row 1, multiply it by a -2, and take row 3, and don't do anything to it, and add those two rows together. And whatever we get, put that into row 3 of the new matrix. So what you're going to do, we're going to take row 1 and multiply everything there by a -2. And again, what you're going to notice is that multiplying the -2 by the +2 will give us a -4. And when I combine it with the +4 that's in row 3, well, they cancel each other out. So let's see, I'm going to go ahead and just put this to the right here. So -2 times +2 gives me a -4, a -2, a +2, and a +6. And we're not doing anything to row 3, but we're going to add it to row 1. So 4, 3, 2, and where are we at here? 3. We're going to just kind of add those things together. And so we would say, okay, well, these are 0. Combine your next numbers, and that's a +1, a 4, and a 9. And this is now going to become our new row 3. And so what we would wind up with, and I'm going to go ahead and kind of put this up here at the top. Row 1, ultimately, we didn't do anything to it. This is a 2, a 1, a -1, and a -3. The row 2 that we got after we did that first row operation was a 0, a -1, a 5, and a 9. And the row 3 that we got after we did that second row operation is the 0, the 1, the 4, and the 9. Okay? And put our bar to separate the coefficient from the constant matrix. And this is ultimately what we're winding up with as our end result. Now, this is the end result of the two operations that we did. It doesn't quite get us to the point where we could, solve for z right away if we asked to solve this particular system for x, y, and z like you did in the previous example. But you can see if you wanted to, we could simply add the row 2 that we have now to the row 3 that we have now, and whatever that whatever those numbers are, if we substitute those into row 2, or I'm sorry, into row 3, then that would give us that 0, 0, and 0 in the lower left corner that we got originally when we did solving our systems in the previous example. Okay, so that takes care of kind of what we're looking at. I understand that this is a little bit long. There's a lot of information. We're going to do a lot more practice with row operations when we'll spend more time solving systems. But any questions that you had, of course, please write them down. Any thoughts that you've had, again, also please write those down. And any, bring them to me in class, bring them to me when you come to tutoring, and I'll be happy to talk with you about them. And until then, guys, thanks for watching, and we'll see you in class soon.